Hello everyone, this is Manohar Reddy, Department of Cybersecurity, Institute of Aeronautical Engineering. Today I am going to discuss about the concept of central limit theorem in probability theory. So probability theory, we already know that all the different types of problems can have the different probability problems. So in that we'll have different types of problems, and among that all the problems, one solution is central limit theorem. So the central limit theorem is going to find the different types of means, standard deviations and the variance of all the probability criteria. So let me see how the central theorem will help us to find the probabilities. See, central limits theorem. So the name itself, it contains the random process, it contains the random variables. So here x1, x2, x3, xn up to xn, these are all, you can say that random variables or random samples. So random variable where capital X denoted, random variable is denoted by capital X and it is from sample space S. So the variable which is taken from the sample space is called as random variable or random sample. So x1, x2, x3 up to xn or n random samples drawn from a population with overall mean mu. So this symbol is indicated as mean, and finite variance sigma square. So this is the mean and this is the sigma square is the variance. And if x is a sample mean, x bar is a sample mean, then the limiting form of the distribution is, you can write it as a z equals to limit n to alpha root n of x bar minus mu by sigma square. This is the formation, and this formation, the limit theorem distribution formation, and from here x bar is the sample mean, as we mentioned here, x bar is the sample mean and mu is the mean, overall mean, and the variance is the sigma square is the variance. Then the limiting form of distribution is this one. So limit n tends to infinity root n of x n bar minus mu by sigma square. So the theorem is key concept in probability theory because it implies that probabilistic and statistical methods, so that will have the proofs on both probabilistic and statistical methods that work for normal distributions can be applicable to many problems involving other types of distributions. So different types of distributions to find or to work for the normal distributions. So these probabilistic and statistical methods can be used with the help of this limiting theorem. Suppose that a sample is obtained containing many observations. So among all the many observations, a sample is obtained, like tossing the coins or rolling the dice. So these are all the different samples having that observations, right? So we are getting some samples from that all the observations. So it is obtained, then each observation being randomly generated. So each observation, whatever we get, like a head or toss or like a 2 or 3 from the dice, so is randomly generated in a way that does not depend on the value of the other observations. And that the arithmetic mean of the observed value is computed. Arithmetic mean of the values are computed. So if this procedure is performed many times, the central limit theorem says that the probability distribution of the average will closely approximate to the normal distribution. So this entire theorem is going to say that the probability distribution of the average will closely is related to the normal distribution, So finally we are going to say that to find out the normal distribution or probability distribution, to identify this all the different sample means, variance and mean, overall mean of the distribution. So that is what we have to mention here. To find the normal distribution of the probability of the normal distribution of the problem, we can have this all the means, variance and the sample mean. So that represented x bar, mu and sigma square, right? So that is the standard normal distribution form. So finally we are saying that to find the normal distribution of the given mean or variance or sample mean, we go for the central limit theorem. We have to go for the central limit theorem. So that is what we mentioned here, right? So we'll see how it is working. So the central limit theorem state the central limit theorem. So how we are going to state that? So let x1, x2 up to xn be the random variables with the expected values is exi equals to mu less than infinity and variance 0 less than variance of xi. That means 0 less than variance of xi less than equals to sigma square. That means you can write simply 0 less than sigma square less than infinity. You can write like this way. Then the random variable zn equals to, you can write x bar minus mu by sigma by root n. That is also, you can rewrite it as root n of x bar minus mu by sigma. Like the way also you can write it. Like the way you can write it, right? So to standard normal random variables, as n goes to infinity, that is limits n to the infinity, p of zn less than or equal to x equals to pi of x for all x belongs to R. So all the rational numbers are relational numbers. So we'll mention that pi of x. So where pi of x is the standard normal form. So this is what we have to go to the statement of central limit theorem. So where x bar is the sample mean, mu is the overall mean and sigma is the variance, then n is the any number, then we can rewrite it as the formula zn equals to x bar minus mu by sigma by root n. So the mean of the population of means is always equals to the mean of the parent population from which the population samples were drawn. So whatever the mean of population is identified, which is equals to the mean of the parent population from which the population samples were drawn. So however the population samples were drawn, so from these the mean of the parent population is going to be found. And the standard deviation of the population of means is always equals to the standard deviation of the parent population divided by the square root of the sample size n. Parent population divided by the square root of sample size n. And the distribution of means will increasingly approximate a normal distribution as the size of n samples increases. So finally we are going to conclude this. All the statements are the mean of population, the standard deviation and the distribution of means will follow this formula. So this is the way you can state the central limit theorem. We'll see one problem. So from this problem we are going to find the central limit theorem of values. How we are going to find the normal distribution of this problem. See here. So a bank teller serves customers standing in the queue one by one. So the customers are going to be formed in a line or in a queue. Suppose that the service time xi for the customer I has mean exi equals to 2 minutes. So the mean is given exi equals to 2 minutes and variance of xi equals to 1. So the variable of xi equals to 1 they given. So we assume that the service times for different bank customers are independent, right? So obviously some banks are going to be waiting them for 5 minutes, or some banks are going to be waiting for them for 10 minutes. So depending upon the bank and bank timings, the customers are independent. So let y be the total time the bank teller spends serving 50 customers. So find p of 90 less than y less than 110. So we need to find the probabilistic range, normal distribution range. We need to find out for the 92 less than 110 customers. So how we are going to find this? So for that, what we need to do is we need to identify the formula first. So y equals to all the random samples were added. So x1 plus x2 plus x3 up to xn. So from the given problem where n equals to 50 customers and exi means mean. So the mean they given as 2 minutes and the variance sigma square they given as 1. Thus we have to substitute these all the formulas in the formula. Formula is what? X bar minus mu by sigma of root n, or root n. You can write like this. So or else you can write root n sigma also, right? So now substituting all these values into this form, So see here, what we need to do, we need to find the probabilistic range, that is normal distribution range for the 90 to 110 minutes, So substitute them. So finding of p of 90 minus n mu by root n sigma less than y minus n mu by root n sigma less than 110 minus n mu by root n sigma. So for this one x bar equals to 90, for this one x bar equals to 110. Now substitute all these forms. So 90 minus n means 50. So 50 into mu means what? 2. So 50 into 2 is nothing but 100. And this one is common. So we need to find the range, right? So we can have this keep like this only. And from here 110 minus n means 50 into 200. So what will we get here? 90 minus 100 is nothing but minus 10 by root 50. Minus 10 by root 50, and here it is same, and here 10 by root 50. So minus 10 by root 50 is simplified as root 2, and 10 by root 50 is simplified as root 2. So how we are going to have it means, so root 2 into root 5. So that is nothing but here we can write it as root 2 into root 25 is nothing but 5 square. So square cancel, and this value is getting root 2, right? So see here, the values are the normal distribution range is p of minus root 2 less than y less than root 2. So this is the range we need to find. So to find this range minus 2 to plus root 2 minus root 2 to plus root 2, what we need to write like this. So pi of root 2 to pi of minus root 2. So we need to find the range of this one, pi of root 2 to pi of minus root 2. So to find this range of the values, we need to go for the normal distribution range format. Normal distribution range table is there. Normal distribution range table is there. So we have to see the table and we have to find this value. So pi of root 2. So pi of root 2 is nothing but root 2 value is what? 1.414, right? 1.414. So in the normal distribution logarithmic table, 1.414 value. We need to get 1.414 value. So see here, 1.414 value is what? So this is all negative values of standard normal distribution range, and this is all positive values of the normal distribution range. So 1.4 1.414 is the root 2 value, so that you can write as 1.4, and then next 0.14 like the way you can write. So for this 1.4 is where see here 1.4 is this range. So and 0.14, so 0.14 is nothing but 0.1 is here. So we need to take this value as 0. This one, so 0.92073, 0.92073, and the same value is going to be taken minus 1.414. So minus 1.414 is what? So minus 1.4 and minus 1.4.01. So what is the value of 0.07927? So 0.07927. So subtract these two values. Subtract this value from this value. What you will get? We'll get this 0.8427. 0.8427. So like the way we have to find the range of the normal distributions. So ultimately central limit theorem states that to find the normal distribution range of the given samples along with the given variance and along with the given mean. So finding the mean is one task, and finding the variance is one task, and finding the overall mean is one task. If they given all these means and samples and everything, so the central limit theorem is going to find a normal distribution range is very simple. So like this way we have to find the normal distribution range of the values. So these are all the different normal distribution values for the negative values, and that means minus values, and these are all positive values. Right? So next we'll see another problem. See here, a manufacturing process produces cylindrical component parts for the automotive industry. So a manufacturing process produces cylindrical component parts for the automotive industry. So it is important that the process produce parts having mean of 5 millimeters. So here they are giving the mean is 5 millimeters. And the engineer involved conjectures that the population mean is expected the value is 5.0 mm. So the population mean they are giving and normal mean they are giving, right? An experiment is conducted in which 100 parts produced by the process are selected randomly and the diameter measured on each. So it is known that the population standard deviation. So that sigma is 0.1. So they are giving mean and overall population mean and sigma's variance they are given. And now the experiment gives a sample average diameter x bar equals to 5.027 mm. X bar equals to 5.027 mm. So does this sample information appear to be support or refute the engineer's conjecture? So whether it is supporting to manufacture with this all the parameters or not. So we need to give the information on the paper, right? So how we'll see? So we can take this all the parameters, and in other words, so we can obtain x bar greater than or equals to 5.027 for the sample size n equals to 100. So if the population mean is mu equals to 5.0 mm, right? So mean mu is given, n is given, and x bar sample mean is given 5.027, and the last one is mu is also given. So we need to substitute these all the values. So what is the formula? Z equals to x bar minus mu by sigma by root n. So substitute these all the values. So we can substitute them. X bar is what? 5.027. minus mu value is what? 5.00. So 5.00 here by sigma is what? So sigma is 0.1 by n is what? 100. So root 100. So by simplifying this all the values, 2.7 will get. We have to get the 2.7 values will get. So now what they are giving? Does this sample information appear to support or refute the engineer's conjecture? So whether it is supporting at what type of parameter, at what type of range they are giving to support them. So we need to find this range. We need to find this range that the manufacturer support to refute the process. So how we are going to see it? So P equals to P of Z greater than 2.7. So if it is the range is 2.7 greater than, so if it is the range is 2.7 greater than, then we can say that it is supporting to manufacturer. So see here, so P of Z greater than 2.7, that is nothing but you can write it as a 1 minus P of Z less than 2.7, P of Z less than 2.7. So 1 minus, so 1 minus 2.7. So the range of 2.7 from this table you have to see here 2.7 range. So 2.7 range is what? 0.99653. So 2.7 range is what? 0.99653. So 653. So that is what we write here, 1 minus 0.99653. And the value is what? 0.0035. 0.0035. So like the way you can suppose to say that with this range of the values, with this range of probabilistic distribution, normal distribution range, the manufacturer can support to manufacture all these automobile works. So manufacturing support all this automobile works. So like the way, if the problem is given for all the sample means and variance and number of size and all they given, then we have to substitute all these into the formula. So finally we will conclude that so central limit theorem gives the normal distribution of the given problem. So that is about the central limit theorem. Next, we are going to see that a random process. So we already know that random variable. So we have to do the process also. So random process. So normally there are two types of process. One is sequential process and random process. So sequential process is nothing but the process will follow step by step, or the process will follow sequential manner, right? But the random process is not at all following a sequential process. So why? So see here, the random process is a collection of random variables x of s comma t. So x of x comma t is nothing but you can write it as this one. So on the time of t, the sample spaces are taking, and this variable is called as random variable. So the random variable hold the process, that is random process, and that are functions of random variable t, where s belongs to s, comma s is the sample space, and t belongs to t, where t is an index set. Right? So and another way, random process is a collection of random variables indexed by time. So here we need to remind this one. So the random process is a collection of random variables indexed by time. So based on the time, the random variables are holding that process, or holding that values. And random process is also called as a stochastic process. Stochastic is nothing but continuation of selecting random wise directions. So that is you can say that it is a process. And see here, s of t, that means sample space indexed by time. S of t, comma t belongs to 0, comma infinity. That means that index contains 0 values or finite values or infinite values. 0 values, finite values or infinite values. So this t belongs to 0 comma infinity is a random process, and it is a collection of random variables. This x comma y, whatever the letter you can write in capital, that indicates random variable. So collection of random variables usually indexed by time, or sometimes by space also, sample space also, right? So that is the way you can describe this one. Random process is nothing but it is a collection of random variables indexed by the time from the sample space, indexed by the time from the sample space. So sample space can have all the different types of sample observations. Among that all the observations, obtained observation is nothing but random value, and that random value is holding by the random variable. So that is what we mentioned here. Yes, if t is fixed, so t is nothing but index set. That index set, if index set is fixed with the time, then x of s comma t is a random variable. X of s comma t is a random variable. If sample space and the index set are fixed, then x of s comma t is a number. X of s comma t is a number. If sample space is fixed, then x of s comma t is a signal time function. Signal time function. So if t is fixed, then it is said to be random variable. If t and the sample space is fixed, then it is a number. If only sample space is fixed, then it is said to be signal time function. Right? Here after we denote the random process. We denote the random process x of s comma t. X of s comma t, where x is the random variable and s is the sample space and t is the indexed time. So it by x of t, where the index set t is assumed to be continuous process. Is denoted by x of n, or you can write xn. So a comparison between this random variable and random process seen here. So random variable and random process. So a random variable, a function of the possible outcomes of an experiment. So a random variable is nothing but a function of the possible outcome of a random experiment. So that is nothing but you can indicate it as a x of s. And while coming to this random process, a function of the possible outcomes, of an experiment and also with the time. So f of x of s is only one random variable, but x of s comma t is a random process, because here the random variable drawn from the sample space with the indexed time. So that is nothing but a random process. And the outcome is mapped into a number x. This is what we mentioned here, second point. So if s and t are fixed, sample space and index set are fixed, then x of s comma t is a number. So that is what we mentioned here. Outcome is mapped into a number, and here outcomes are mapped into wave from which is a fun of time t. Outcome is mapped into wave from which is fun of a time t, which is a fun of time t. So that is the way you can understand from all this random process. So random process is nothing but it is a collection of random variables indexed with the time. So that is nothing but x of s comma t. For the random variable, you can directly say that x of s belongs to r. Right? So we'll see here the different classifications of the random process. So we already said that random variable. So random variable is nothing but a variable which drawn a sample from the sample space. A random variable which drawn a sample observation from the sample space. So that random variable is divided into discrete and the continuous random variables, right? So like the way we have classified a random process is also the same types. So see here, we can classify the random process according to the characteristics of time t and the random variable x. So based on the random variable type and time t, based on that random process is going to be classified in the following way. So x equals to x of t and t and x have the values in range minus infinity to infinity and minus infinity to minus infinity and t and infinity. Similarly here and minus infinity, x and infinity, where x is the sample value and t is the time value, index set value, right? So see here, the random process is a function of random variables indexed by the time t. So right, that is what we discussed in the previous slide, right? So random process is a function of a random variable indexed by the time t, indexed by the time t. So random variables are classified into two types. One is discrete random variable and the second one is continuous random variable. So one is discrete random variable and the second one is continuous random variable, right? So discrete random variable is nothing but we can count the number of values. We can count the number of values. But continuous variable, we cannot count the number of values. We can by measuring the countable elements, we can observe that values. And similarly, the random process belongs to the time t also, having the same discrete random process, and another one is continuous random process. Discrete random process and continuous random process. So see here, a continuous time random process is a random process x of t where t belongs to j, so where j is an interval on the real line such as minus 1 to 1 or 0 to infinity or minus infinity to infinity, etc. You can write any of the things. So continuous random process contains the interval of the values that may not be countable. We can measure the range of the values. But in the discrete time random process, it is a random sequence, it is a random process where x of n equals to xn comma n belongs to j, where j is the countable set. So we can count the number of elements and we'll say that. So that contains a random process. So such as n or z. So n or z is nothing but numbers are integers. So numbers are integers, so we can count it. And we can explain it, right? So how many number of elements are there means we can count them. But in continuous time random process, we are not going to count the number of elements. We have to measure them by applying any measuring machines or measuring elements, right? That is about random process classifications, right? And the next one is random walks. So random walks are nothing but, so in a probability theory, a process for determining the probable location of a point subject to random motions. That means random walks contains random motions. That means random movements. So that is all comes under the random process point of view. So the random process is a collection of random variables indexed by the time. Similarly, the random walks it is a function of random process with the different motions, with the different movements indexed by the time t. So see here, the probabilistic location of the point subject to the random motions, given the probabilities the same at each step of moving some distances in some direction. So that means a value is drawn from the sample space is going to be take the moment of either left side or right side or the straight side, whatever it may be. So consider the random movements from the random process is nothing but random walks. So see here, the example is nothing but, So we are going to choose this random process. We are going to choose this random process with moments, random moments. So see here, the person is going to started here. So person is going to be started here, and he comes for the next step for the couple of minutes, and again couple of the minutes he'll move to the next position. Again he'll move to the next position. Again he'll move to the next position. Again move to the next position. At particular point of time, at particular point of time or a particular point of subject, he wants to move either in this direction or either in this direction. If he wants to go this direction with the time t or time t plus 1, if he wants to go with the direction time t, find the probabilities of transitions, find the probabilities of transitions to move the person directed to the directed to the end point. So how they are going to be choose this process, choose this random process with the help of random time, with the help of indexed time, is going to be known about random walks. Is going to be known about random walks. So random walks is nothing but it is determining the probability location of a point subjected to random motions. In simple way, you can say that a random walk is a taking the moments or positions from the random process, taking the moments or positions from the random process. So in the point of probabilistic point. So that is the way you can understand. So to know about this random walks, transition probabilities, we are going to discuss the stochastic process of Markov chains theorem in next coming sessions. Right. So this is about random walks. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.